Welcome back. So up to this point, we've only talked about conductors and insulators, and the vast majority of the materials you're going to run into are going to be either a conductor or an insulator. And you probably remember that a conductor is something that allows the charges to move freely through it, while an insulator resists that movement. There's no such thing as a perfect insulator. You put enough charge and electric field to something, well, those electrons will move. But in general, we can consider an insulator to be something where the charges are just frozen in it. Now, what makes those two materials have the property they have is simply because of the outer shell of electrons that they have with valence electrons. In a conductor, there is either an extra shell. There's an extra slot in the shell where an electron could move through, or maybe there's actually literally another electron. But something allows that, so it's not tightly bound to the nucleus, and so that allows it to go through. If all of the pairs of valence electrons are filled, well, okay, in that case, it's not going to be free to move. And so any electrons that try to come into that material don't really have any place to go. So electrons don't just freely travel through the material, and even though that's kind of what we idealize it to be, in reality, it has to get traded from atom to atom to atom to atom. And so that's why we can determine most metals will have that free slot or electron that we can have that it can just basically trade as it goes across. So what we're going to talk about today are semiconductors. And as the name kind of implies, they're kind of halfway between a conductor and an insulator. And semiconductors are key to pretty much all of our modern electronics. Everything that we have, from integrated circuits to computers to the video that you're watching right now, all of it depends upon semiconductors. So in this lesson, we're going to figure out how do semiconductors work, and then we're going to talk about the most basic type of semiconducting device, a diode, and what it's used for and how it works. All right, well, let's get started. Okay, so follow along in your book here in case these diagrams are kind of hard for you to see on your screen. Before we talk about semiconductors, I want to talk about what goes into making them. And semiconductors are actually made out of silicon. You may have heard that. Silicon is actually one of the most common elements on the earth. An example, like if your beach sand is silicon dioxide, it's basically silicon to oxygen atoms. So it's very, very common. It's very easy to find, and it's really not anything expensive or anything. Just go to the beach, harvest some, and you can get the silicon out of it. But what makes silicon special, if you look at the picture that we have down here, let me get my pen so we can draw that. If you look at this picture here, you see that here we've drawn the valence electrons around, so that each little red dot that you see there is a silicon atom. And the way this works is each one has 4 valence electrons. And so 10 of those, the atomic number is 14. 10 of its 14 electrons are very tightly bound, but 4 of them fill out 4 of those pairs in the outer shell. Well, that means that they can tightly bond to something else. Well, the crystalline lattice here that gets formed is due to the fact that silicon shapes up very nicely. It can share with all of the surrounding silicon atoms that are there, and you get this nice, beautiful crystal lattice from that. Well, we don't have any free electrons here. We don't, or even electron holes from that. All of our valence slots are filled. So silicon is an excellent insulator. And now that may seem strange that we actually use silicon to build semiconductors and to build all our computer hardware. Well, what happens is that we add just a small amount of impurity to it. It's called a dopant, which of course has other connotations in sports and things like that. But a dopant is really just an impurity that's added to something. And one of the most common ones, as we see here, is phosphorus. And phosphorus has an extra valence electron. So it's got 5 valence electrons. Now, so when you look at the picture here, the green ones that I've drawn here, these green ones are phosphorus. And you see that they've got that extra valence electron right there. So that valence electron can effectively be just passed around from one atom to another. It can just get swapped around from one phosphorus atom to the next, and so it can start moving through this. So we can control the amount of conductivity by controlling how much of the phosphorus we add to this. The more phosphorus you have, obviously, the more of those extra little valence electrons you have to move through. And in fact, pure phosphorus would be a great conductor from that. So that's a very useful property. You can have something that only sends a little bit of the current through, but more importantly, it's something that you can control. Now, that on its own might be useful, but that's not actually what semiconductors are generally done. There's another reason for this. So let's take a look at microtask 1 here. And we want to look at the electric field that results. So say we're going to take this little chip of the semiconductor, which semi means halfway in between, and we've got some phosphorus and we've got some silicon, as you can see there. And we're going to connect it to the battery. Now remember that when we're looking at the battery, this end is the negative end and this end is the positive end. So what I want you to do, pause the video, and it's going to be really important that you pause the video and walk through this. Otherwise, students get very confused about how semiconductors work. You really do need to go through these exercises, and then it'll make sense to you. If you're just watching the video, you're going to be like, okay, Dr. K, if you say so, but it's not going to mean anything to you. So what I want you to do is pause the video. I want you to draw an arrow of the electric field inside the semiconductor. And that means you're going to have to label which side of the semiconductor is positive, which side is negative. And you want to remember our rules for drawing an electric field. Pause the video. Do that now. Did you pause the video? Okay. So because just like with our capacitors, this side is going to be negative and this side is going to be positive, just like that. And that should make sense, right? It's because that's what's connected to the positive and the negative terminals. So now if we want to draw the electric field, then remember our rules, Faraday's rules say that always goes from positive to negative. So our electric field is actually going this way. So pause for just a minute and see if that makes sense to you. Okay, then the next question says, in which direction are those free phosphorus electrons going to move as a result of the electric field? The electrons have a negative charge. So what's going to happen to them? Well, you've got a charged particle, you've got an electric field. They're obviously going to move. They're going to get repelled from so if this is my electron, right, then it's going to get repelled and they're going to move. Let's do a different color here. They're going to move to the left, just like that. And that should make sense. That's from what we've learned up to this point. It's a negative charge. It's going to get repelled from that negative side. It's going to start moving towards the positive side. So these little valence electrons then will slowly kind of move through the material and then come back around. All right. So they actually leave the semiconductor. So, I might jump from here and this one, and then this one actually goes out and goes back to the battery. But it's being continually replaced by electrons from the battery. So the total number of electrons that are in here are going to remain constant. So let's scroll up here. What is the net charge of the semiconductor before we connect the battery? It's a little tricky, so think about it. Well, it's actually going to be neutral, right? And that may surprise you because you went, wait, Dr. K, didn't you just say we have extra electrons through here? Yes, but remember that the phosphorus has 15 protons inside it. So the net charge is going to, in fact, be neutral from that. So after I connect the semiconductor to the battery, what's going to happen? What's going to be the charge inside? Also a little tricky, but think about it. I've got electrons leaving the system, and I've got electrons entering the system at exactly the same rate. So if it was neutral before, it's going to be neutral after I connect the battery to it. So this is an important distinction between a semiconductor and a capacitor. The capacitor stores charge. That charge builds up on the two plates. That's not happening here. The electron is just continually moving through, just like it would if it were a wire or a resistor or anything like that. So the only big difference between this and a regular conductor is that the speed, the rate at which those electrons are moving through is dramatically reduced because it's almost a pure insulator, and it's only those dopant atoms that are allowing the free electrons to move across. All right, so we call this an N-type semiconductor. I'll write that. It's written in your book, but we'll write that here. So this is an N-type semiconductor. because the negative charges are what's moving through the system. That should make sense. Physicists don't get out much, not terribly creative name. All right. So let's look at the next possibility. We'll go ahead and delete this one. The silicon or phosphorus is not the only dopant that we could use. Another possible one is boron. And let me, whoops, don't want that. Let's scroll up just a little bit so that you can see this. And so here I've colored yellow the boron atoms that are there. And the boron has one fewer valence electron. Now, remember, it's still neutral because it's a different number of protons than the silicon does. So I don't have any kind of free charge or anything like that. It's still completely inert, completely neutral. But now I've got a hole. Engineers refer to it as a hole simply because it's a place that I could have an electron, let's say this is my electron, could jump in and fill that because it would be more stable. And now then the next one could go here and then here and then here and so on, and it could then move right on out. So the electrons are still free to move through the material, even though there's now not an extra electron. So let's zoom over and let's look at microtask 2 again. So now we're going to connect the battery just like we did before. Notice now, though, that instead of the phosphorus-doped material, the phosphorus-doped silicon, I now have a boron-doped material. So again, we want to label the directions so that we can tell where our positives and negatives are. For the battery, still unchanged. That's positive and negative. Where would the charges, what will the charge of the left side and the right side of the semiconductor be? Well, we've done all this before. That's negative, and that's going to be positive. All right. So which is the direction of the electric field? Use Faraday's rules. You should be sketching this actually on your book so that you've got the place to refer back to, so you don't have to keep coming back to the videos and say, oh, what did Dr. K say? So, right, our electric field always is going from positive to negative. Okay, now electrons from the other atoms in the lattice jump to fill in the hole because that electric field is causing them to move, if you think about that. So which side are the jumping electrons going to be attracted to? So as we showed in the diagram up above, when I have electrons that jump from hole to hole, so from here to here to here and so on, which direction are they going to move? Well, don't be fooled. They're still going to go to the left, right? Because they're electrons. They're going to get repelled by the negative. So the fact that it's a hole instead of a free electron actually doesn't make any difference in how that electron is going to move. Now, the properties are going to be very different by the time we get through with this. But for now, I want you to look at this and you should see that, yes, the physical thing that's moving is still that electron, and it's just jumping from one hole to another hole to another hole to another hole. Okay, so, and then as we say, eventually the electrons move out of the left side, out of the lattice, and back into the circuit wires. They're being replaced. So just like before, the battery's coming around and filling them up. So, same question as before. What was the net charge of the semiconductor before the battery was connected? Well, it's going to be neutral, just like we decided, right? Because even though it looks like I have one fewer, you might be tempted to say, oh, well, I must have a positive charge because they've got some fewer electrons there. But remember that the boron has fewer protons as well. So overall, the total net charge of this is going to be 0. What about after we connect the battery? Same situation. Yes, I have electrons that are leaving the lattice, but they're being replaced at the exact same rate by electrons that are entering the lattice. And so the net charge, even after I connect the battery, is still going to be neutral. So what you want to ask yourself now is, do the boron atoms actually move? And stop and think about that. Are there any, the boron atoms are those yellow little circles that we have there, are they moving through the lattice? Well, it should be pretty obvious that no, they're not moving, right? They're stuck in the lattice. It's the electrons that are moving. And you may say, well, okay, yeah, that's obvious. Why would we care so much about that? Well, what happens is it appears that these holes are jumping from the right, so that as the electrons jump from left to right, then it's going to appear that the holes are actually moving from right to left. And that's hard for me to show without an animation. But if you think about it, if I have an electron that fills this right here, well, that hole is now gone, right? But I could have one that was leaving from where this one was, and it could travel over here, the hole that is. And so the hole seems to progress across the lattice. Now, remember, the boron atoms aren't actually moving. But so try to sit there and think about, if I've got an electron filling the holes, what does it look like the hole is doing as it moves across, right? So again, the hole is not actually moving, but it appears to be that way just because of the way the electron is. So it looks like the positive charge is moving through, that hole is moving across, even though it's not. Then I want to stress that. So for that reason, we refer to this as a p-type semiconductor. And it's because the positive charges, those holes, seem to be the ones that are moving. When, of course, remember, it's the electrons that are moving, but those holes seem to be moving as the electron moves across. So all of these characteristics then are basically what takes just a lump of silicon that won't conduct electricity. It's those dopants, remember, that are allowing it to conduct the electrons as they go across. Now, a semiconductor on its own is not terribly useful. I mean, yeah, sure, you might say, well, great, I can control the amount of current going through there, but we've got an easier way to do that. It's called a resistor. So why then are semiconductors so important? And the answer to that is because of semiconducting devices. It's when I take two or more of these semiconductors and put them together that's where the magic really starts to happen. So let's take a look at that. And this is the next section in your book. The most simple kind of semiconductor is semiconducting device is a diode. So let's bring that over here. So pull this up in your book so that you've got it available here. So with a diode, we're going to take one of each of the different types of semiconductor materials. So we've got a p-type and we've got an n-type, and we're going to put them together. So when we look at that, then where they meet, in this region where they meet, and what I'm going to do is I'm just going to blow this area right here up, and that's what you're seeing right here. So this region that I've drawn in here is actually just on the surface of where the two types of semiconductors come together. And so let's take a look and see if we can analyze what's going on with this, and it'll give us an idea of how all of these different devices work. Okay. So what happens is we've got these extra electrons, the free electrons, from the n-type conductor that move into the p-type semiconductor and fill those holes with that. All right. So what is the electric charge in the center where these two meet? Well, it's going to be neutral. It's still going to be neutral. The whole device is electrically neutral because we have the same number of protons as we have neutrons. However, in this region right here, it's completely neutral. I don't have any kind of electric field from that because I've filled everything up, and so that's called a depletion region. And that depletion region is really very, very small. It's just basically on the surface where these two things meet. So when it forms, and this is what we're talking about here in microtask 1, when it forms, there's extra electrons that made it all the way to the p-type. So I'm not talking about in the depletion zone, but I'll have some electrons in this region that have filled in maybe a few of these holes here. And so I'll have a net effect of having some extra electrons with that. And then obviously on the n-type side, I'm going to have just a few less electrons. So take a look here. It says, what is the net charge on the left side of the depletion zone? I've got some extra electrons. And we're talking about just on this side, not the device as a whole. Well, it's going to be negative because I've got a few extra electrons. And again, I want to stress the device as a whole is electrically neutral. But right there in that little region where I have just a few extra electrons that have come across, then I'm going to have a net negative charge. All right, so take a look at the next part of that microtask. It's on the next page here. So what is the charge on the right side? Well, okay, you should be able to figure this out, right? We've had some electrons leave, So what's a charge just on the right side of that? Well, it's going to be positive, right? Because we've had some electrons that have left. So the overall charge is going to be positive. So now what we want you to do is we want to say, what is the electric field in the depletion zone? And I'm not going to draw that whole lattice, but I'm just going to sketch my two pieces here. So here's my depletion zone. This is my p-type, and this is my n-type. We've decided that we have a very, very slight negative charge here and a very, very slight positive charge here, because those electrons have left. They've jumped across then through and filled in some of these holes here. So what would my electric field look like in that case? Well, our field lines always go from the positive to the negative. And so, following Faraday's rules, they're going to go right to left. So I have a very, very tiny electric field inside there. Okay, so as a point, this device is called a diode. We've actually seen several of those. We'll talk about this in just a minute. And here's the electrical symbol for it. This is what the symbol that you would use in your electric circuits. And we'll talk about how that works here in just a minute. So why would we care? Well, the end result is that a diode only allows current to flow in one direction. If I connect my battery in one way, I'll get a current that'll go through it. If I flip my battery, then actually the diode will stop that current from coming through. And that can be really useful. Let's say that I want to protect my main board from current coming back through it. I can have this diode so that it only allows current to go out, but doesn't allow current to go back in. So let's see if we can figure out how that process actually works. So let's go down to microtask 2 here. So I'm going to connect a battery here so that I have a circuit. Now, what direction is the electric field in the depletion zone? And I'll give you a really good hint there. Yeah, well, it hasn't changed, right? So because that electric field is strictly due to those electrons in the two semiconductors being attracted and jumping across that depletion zone. Now, what is the direction of the electric field due to the battery in the semiconductor? Well, let's make sure this is negative, this is positive. So the electric field due to, in my semiconductor, looks like this due to the depletion zone. But due to the battery, it's going to look like this. It's going from left to right. So I have this tiny, tiny, tiny little electric field inside that's opposing this great big huge electric field coming from the outside with that. All right, so that's going to be an important key. Let's go to the next one here. So what direction is the battery going to push those holes in the p-type semiconductor? Make sure that you've got your book, because obviously I don't have both of them on the screen at the same time here. But think about it. I'm going to have, let's use our diagram here. I've got a very small electric field inside due to this depletion zone. And then I've got this great big one from the battery. Now remember, electric fields are a vector. What is the net electric field? Well, the net electric field, we'll do that in a different color. The net electric field is going to be just slightly weaker, but it's still going to be in the same direction from here. So which direction are the positive charges going to want to move? The positive charges. They're really the holes. So the holes are going to seem to go from left to right, because remember Faraday's rules, the positive charge is going to follow those electric field lines. And so which direction is the battery going to push the electrons, the actual electrons, in the n-type semiconductor over here? Well, because of this electric field, right, they're still going to go this way. So they're going to go from right to left. So since this electric field is so much stronger, then the free electrons will move through the depletion zone. Now, they don't want to, but it's very weak because it's very small. And I've got this huge, huge, huge electric field. So the net electric field is going to be from the left to the right. So my electrons will move from the right to the left. Current can flow. And let's stop and think about that. I've got two electric fields. One is due to the slight extra electrons that I have on this side and then the holes that are on the other side. So it's very small. However, I've connected it to this battery, and that's probably a terribly drawn battery, but we'll do it like that. That's producing this very, very large electric field. And since it's a vector, I add these two together and I have a net electric field pointing from left to right. Remember, this shows how the positive charges move, but it's actually a negative electrons that are moving. So the negative electrons are going to go from right to left, current flows. All right, make sure that you've paused the video and that makes sense to you. Don't just accept it, because this next part is going to be really important. Okay, so now let's look at microtest 3. Now, suppose we're going to reverse the battery. So now my negative pole is over here and my positive pole is over here. So what is the direction of the electric field in the depletion zone? Remember, it doesn't change because it's not due to the battery. We'll do that in red. And that is still going to be right to left, just like that. Now let's look at the direction of the electric field due to the battery. Now, keep in mind, now this side is negative and this side is positive. So what's the direction of that electric field? It's helpful to draw it on your diagram, but yeah, it's going to go this way, right? Which is the opposite direction for what it went before. So it is also going to go right to left. So how are the positive charges of the holes going to move in the p-type part of the semiconductor? Well, remember, I have to have the net electric field. Well, now I have a super strong electric field moving this way, which means that I'm going to collect. So it's going to be from, let's go back to black. That's going to be from right to left, because that's showing how my positive charges are going to move. So those holes in the p-type are going to get pushed even farther over here. So they're going to get pushed even farther in this direction, I should say. Okay, so which direction is the battery going to push the n-type, the electrons in the n-type semiconductor? Well, remember, they move opposite to the arrow, so they're going to get pushed this way. So the end result then is I have even more positive charges moving away from that depletion zone and even more negative charges moving away from the depletion zone. And the end effect is the depletion zone, instead of being teeny tiny, gets very wide. And it gets so wide that no electrons are able to cross. In fact, the electrons are wanting to avoid the depletion zone from that, as you can see. So if I put my battery in backwards, then no current's going to flow across it. And this is why the diode only allows current to flow in one direction. For completeness, we'll go ahead and make sure you circle that. Yep, so it's moving from left to right. Okay, I'm not going to read this part to you, but basically the important thing that we're going to find with this is that the diode is going to restrict the current. So let's talk about how to draw a circuit with that. So we'll start off with, let's put our battery back going this way. And then the symbol for it, I'll draw it over here so that we don't get confused. This is the symbol for a diode, and usually that's colored in black, but we're almost never going to do that. So I'm just going to draw that like this. Now, if you look at your description here, down in the second paragraph, it says that the positive terminal is called the anode. So the part that's connected to the positive terminal of the battery. And so that's the part that is represented by this triangle right here. So that's the side that's going to get connected to the positive part of the battery. The negative part is called the cathode, and that's going to be represented by this line right here. And so that's what's going to get connected to the negative terminal of the battery. And so in this direction, then, current will flow. If I wire my diode in the other direction, because I don't usually want to flip my battery, but let's say that I keep the battery in the same direction like this, but now I'm going to have my diode looking like this, and no current will flow. So that's the important way that we can distinguish these. So on the actual physical piece, Generally speaking, they're going to label the cathode by a stripe on there. And remember that that's going to be, the cathode is your negative side. So that's the side that's going to connect to the negative side of your battery or to ground or whatever you happen to need. So it's really important that you look at the diode and look at it physically to say, okay, where is that? Now, the diodes are actually very tiny. They look like little resistors, and they'll have this little band right here attached to it. Often these are black and they'll have kind of a silver band. So you can think of that band as being equivalent to the line from that. So that's going to be the cathode. Okay, now we mentioned that there's no concept of diodeness in the way that there is for capacitance or resistance or things like that. Instead, there is a certain amount of voltage that's needed to overcome that depletion zone. Remember, if I don't have a strong enough electric field, then that depletion zone is going to fight so remember I had my depletion zone going this way, and I needed a big electric field going in the other direction, depending on which way we've got our system organized. But if it's not big enough, then current won't flow because the electric field due to the battery will be smaller than the electric field due to the depletion zone. And so in that case, I don't have enough oomph, I don't have enough electric field to force it to jump across. The net electric field is not going to be in the correct direction for that. So the voltage that's required to produce the electric field that's required to get the current to flow is called the forward voltage of the diode. So if you don't have at least that amount of voltage going through the device, going through the diode, then no current's going to flow. And the most practical application of this is with an LED. An LED stands for a light emitting diode. Now, all diodes emit light. They all have a certain amount of resistance. And also, as those electrons drop into holes, they're in a lower energy state. And so they're going to radiate out some energy. And generally, it's going to be infrared. Almost all diodes are going to be infrared diodes. And those aren't useless. And in fact, the infrared diodes are what you've got in your remote control, for example. When you point your remote control at a television, it's actually sending infrared light, and then there's an infrared receiver in your television that interprets the pattern of flashes to do what you want it to do. So that's a light emitting diode. It's just not light that you can see. So typically an LED, we mean one that's visible light in a certain color, and that has to do with what kind of energy drop we have. The different kinds of energy loss is going to correspond to different wavelengths, different energies of photons. So we can control the color of the LED by determining what that drop is when those holes get filled. But even then, we still have to have enough voltage to force those electrons to move through the device, because if there's no current going through it, well, then there's no energy and the thing's not going to light up. So that you can think of that forward voltage as to be kind of the minimum operating voltage that the device needs. But now you know that what it's really for is to get an electric field strong enough to overcome that depletion region. Now, and again, if I put my diode backwards, it's not going to fry. Nothing's going to happen, because what's going to happen is you're going to increase that depletion zone to the point where no current at all flows through. And so it doesn't matter what its voltage is, nothing's going to happen. It's just going to go straight on through. So think about these different types. Think about the LEDs and the different colors of LEDs, how that works. They're different colors not because of the little clear colored dome on there, although that does reinforce the color. It's because when I drop into that energy shell, that's the amount of light, that's the wavelength, the energy of light that I'm emitting. And again, infrared LEDs are not useless. We talked about how you use them in your remote control, but in the case of robotics, your line following sensors are going to be infrared LEDs. It's going to send that infrared light out. It bounces off the paper or whatever it is. And then right next to it is an infrared detector that's going to see if it's getting that light back. So lots of applications for diodes. Diodes are used pretty much everywhere. This is how we can convert the AC current coming from your wall into DC current that's going into your computer. Your computer won't run on AC current, but we can convert that using diodes and making things only go in one direction. We'll get into that later on. Okay, so now you've learned how diodes work, and the key to the diodes is that they're made of these semiconductors. Without the properties of these semiconductors, the diode simply wouldn't function. Diodes are not the only kind of material, the only kind of semiconducting device. There's a lot of different ones out there. And in our next lesson, we're going to look at probably the most important of all of these semiconducting devices, and that's the transistor. A transistor is what makes a computer work. It's what powers its logic. It's pretty much everything that we do when it comes to modern electronics is going to be based around transistors. So tune in then, and we will get into a whole lot of detail about this semiconducting device. We'll see you then.